Okay, but what I had been discussing and didn't quite finish last time because I didn't want to rush it was quantifying this approximation of the reduced Hartree-Fock and the Hartree-Fock effect. So I will just remind you of this bound that since Hartree-Fock was restricted to certain file space, which is the state of the permanent, and reduced Hartree-Fock was ignoring a negative term, the exchange term in Hartree-Fock, then we have inequalities like that. The quantum energy is less than the Hartree-Fock, less than or equal to the Hartree-Fock energy, which is again less than or equal to zero. I mean, clearly these inequalities will be solved, but let me not discuss that. Okay, so now we wanted to get a lower bound, and I will be using, I did it already last time, the Lieb-Thering inequality, and Robert has promised, or he's promised me, to prove the Lieb-Thering inequality, so I feel good about using it. And you will just see, and then you will be much more motivated to see the proof of this inequality later. And then we discussed last time how by keeping a little bit of the kinetic energy, splitting the kinetic energy in two, and keeping some of it for what I call the rainy day, we could actually get estimate on the quantum density, the Hartree-Fock density, the reduced Hartree-Fock density, all of them to the 5/3 would be bounded by, if I think of neutral atoms, v to the 7/3. So we have such an a priori bound on the 5/3 norm, but if it's 7/3, it's the 5/3 integral that is bounded by v to the 7/3. And we were going to use this in getting the bound on showing that the quantum energy is not only bounded above by reduced Hartree-Fock, but also bounded below by reduced Hartree-Fock, of course with an error, because the upper bound is without an error. It's a strict upper bound that quantum energy, total quantum energy of an atom is less than or equal to the energy of the reduced Hartree-Fock energy. I want to get the lower. And if you remember what I did, I approximated, bounded the Coulomb by the interaction of two balls. So I smear out the electrons to balls of radius A. Instead of being point charges, I made them smeared charges and looked at that interaction. That interaction will be smaller, but not if the distance is large enough, the two are actually the same. That's what I wrote up here, that the WA of X is actually X to the -1 if the distance is large enough. And if the distance is smaller, then it's actually smaller than X to the -1. And it is fine. And then I used the fact that it had a positive kernel, so that the Fourier transform of WA was positive. So I could, when I have first, this lower bound follows simply because the W is bounded, X inverse is bounded below by W. So then I get this lower bound. Here I'm summing over all pairs. But instead of summing over all pairs, I can actually sum over all particles, including the self-interaction, because that's no longer infinity. Right? Over here, it would be dangerous to set I equal to J, or you would get infinity. But here, infinity is bounded below by something finite. But here I'm actually giving a bound, namely that at 0, I can replace it by Ca to the -1. So if I include and then sum over all particles, including self-interactions, I'm just overcounting by this one. And the advantage of doing this is that this kernel is positive, and then I can put in a trial density. I can think of delta, this empirical density, the sum of the delta functions where the particles are. This is all classical. This inequality is classical. And this is a classical electrostatic inequality. I sort of approximate where these particles are by a smoother density. I can subtract that in both places and then make up for the errors. So I just smuggle it in at these 2 points. And then I'm making an error that where the rho tilde with the x's, that comes in twice. Or the rho tilde with itself, those terms I have to subtract. Right? The rho tilde with the x's comes with the minus sign. So therefore, I have to add in the thing I had the mistake, and the row tilde comes in with a plus, so I have to subtract it. So these two terms make up for the errors I made up there, and this error makes up for the fact that I included it there. And now I use that it's a positive kernel, has positive Fourier transform, so this quantity here is positive. And I throw it out for lower bound. It's actually useful to remember that we throw it out, because this means that if we get a good estimate in the end, it must mean that this cannot be so positive after all. So one can actually get an estimate on this quantity from the fact that the lower bound reacted. So one could come back and use that, and this has been done, but I will not do it. So I wrote it down there. This is a lower bound on the Coulomb repulsion between the particles in terms of a one-body potential, right? Each particle, it's really like a mean field lower bound. You're bounding the complicated interaction of all the electrons by a potential where each electron sees the field, the same field, all of them. So you actually get a mean field lower bound. These two terms I actually just found. Okay, and then you plug it into the Hamiltonian, you replace the 1 over xi minus xj by this one-body potential and then the two constants. And now you would like to here go back and actually get the right mean field, meaning that you would like to now replace the WA back with the x to the minus. I put in the smeared electrons to be able to do the bound. Now I want to remove it again. So that needs an estimate. But if you think about how it will appear up there, this will be when you take an expectation value against the state, which is what I'm doing down there, then it will actually be this term there integrated against the density of the. So I basically need to estimate the difference between what I would like to have, the rho tilde convolved with x minus 1, and the rho tilde convolved with the smeared out thing. This difference, I have to understand how big is that when it's integrated against some density. And that density will be the true quantum density. And here I simply use the fact that, well, I mean, both of these terms are convolution terms, right? So the first term there could be written like that with no restriction. If you forget the restriction here for a second, then this thing is actually that first rho tilde star x inverse against the wall. So how come I can remove how come I can forget that term? Well, this I can forget because it's positive and it's being subtracted. But I ignore this only when x minus y is less than 2a. Because with x minus y is bigger than 2a, then the two terms are the same. This is actually x to the minus. So I can get an upper bound by this. And here I can then use the Hölder or Young's inequality, which says that I can estimate this integral by this in a p norm, this in a q norm, this in an r norm, if 1 over p plus 1 over q plus 1 over r is equal to 2. Right? So I choose the powers 5/3, 5/3, because those are the ones where I have the a priori bound, 5/3, 5/3, 5/4. Right? So 1 over p plus 1 over p, 1 over p plus 1 over q plus 1 over r is 3/5 or 3/5 or 4/5, which is altogether 10/5, which is. Okay, these two terms actually, well, I just copied them here, but I will use in the end that we have a priori bounds on this. But here's the general list. That integral you can do, it's a finite integral and it gives you a to the 7. So that's an it. It's a constant times a to the 7. You can do it explicitly. So therefore, we conclude up there that I can replace the WA by the rho tilde star x inverse if I use this estimate there with rho replaced by the density of the flux. So I get the estimate rho psi 5/3, rho tilde 5/3, a to the 7/5, and it's two same constants. This is my knowledge. And as I said last time, this is the correct lower bound for any rho tilde. And I will actually use it for two different rho tildes. I will first choose the best possible, and then afterwards I want to choose one which is not the best possible, but still quite interesting, namely the Thomas Fermi thing. But first, the best one. And the best one is actually to use the reduced Hartree-Fock limit. So let me just explain that briefly. So I just copied it again up here. That is the inequality from before, except that I said I don't know what the gamma psi is. The gamma psi is the one particle density matrix of the true ground state. I don't know it. But I know that you can never get anything here smaller than what you would get by taking the sum of all the negative items. To be projected onto the negative part of the space. And that's what I wrote there. This is the trace of the negative. Gamma is an operator with eigenvalues between 0 and 1. So the smallest you could get is by choosing the worst case gamma is the one that has eigenvalue 1 for all the eigenfunctions in the negative spectrum of the operator. And that gives that a lower one. Okay, and then I can ask myself, well, in this problem, what is the best road type? Now, so let me not really go through the full argument, just try to argue that reduced Hartree-Fock is actually the best. Because if you do a variational argument here, forget this row tilde there. Because there I'm just going to estimate it to be Z5. Whatever you do, you're going to estimate integral row tilde 5/3 to be Z to the 7th. Of course, one could also try to include that in the optimization. But at this point, I just want to say what optimizes those two. And you see, if you just do a derivative in the row tilde, then up here, this is from what's called the Feynman-Hellman variational principle. Right? If you vary the potential, the variation in doing that is the potential estimated on the ground state. So if you estimate it on the ground state, here you would get the row tilde integrated over some row gamma, where the gamma is the projection onto all those negative eigenvalues. And that would mean that this term, this derivative would actually become this integral here, integrated against the row. I mean, if you vary the row tilde, it becomes, you're varying it locally, and the variation would become that function. If you vary this one locally, the variation will become rho tilde star x inverse, right? This is a square, so when you take the derivative, it comes down here, kills the 2, and this is what. So to get a derivative that's 0, I would like those two to be this. And how can you get those two to be the same? Well, to choose rho tilde to be rho gamma. So in other words, you are looking for a rho tilde with the property that when you project onto the negative eigenvalue, the density you're getting for that projection is the same as the one you started with. This is what's called the self-consistent condition. You want to choose rho tilde so that the density onto the negative eigenvalues is rho tilde again. And that's exactly the sort of Euler-Lagrange equation for the reduced Hartree-Fock. So the best choice you can do is exactly to do that, the reduced Hartree-Fock. So that's what I'll do. So I'll plug in the reduced Hartree-Fock minimizer. Can we, how do I remove this? Oh, okay. Sorry. So, remember that we know that if we choose rho tilde to be the reduced Hartree-Fock minimizer, then we know that both of these is bounded by Z7 first to the 3/5, because I'm now doing the norm, which is Z to the 7th. So now I can plug in everything. I now know that the lower bound on the psi HZ psi is the reduced Hartree-Fock minimizer. So I put in a mu here because I want to study the neutral atom. But the neutral atom is not the full minimizer of reduced Hartree Fock. I ignored that a little bit in the argument before, but you really, strictly speaking, have to put in a mu right there because you want to fix that you're doing neutrality. I could also say that I look at the absolute minimum, and that means the energy of the atom that has the largest number of particles. But that's not, I want to do the neutral atom, and therefore I have to put in a plus mu. To ensure that I'm getting the reduced Hartree Fock. Right? But here all I did was I added and subtracted it. So I did not, I haven't made a mistake at this point because I just added and subtracted the same thing. But the reason I'm doing it is that I would like to minimize this and get the thing that corresponds to the absolute minimum. But I can also do it for any other number of particles. But the argument I gave before was for the absolute. Okay, so now let's put all the things together. So here I'm getting I'm using the fact that I have the sum of the negative eigenvalue of reduced Hartree Fock, and I know from the variational principle of of reduced Hartree Fock that this and that together is exactly the reduced Hartree Fock. So this term is actually included with that term to give the reduced Hartree Fock energy. That's the variation problem again for reduced Hartree. So altogether, I'm getting, all of these three terms together will give the reduced Hartree Fock. The role of mu is just because I'm looking at the neutral atom. Or any other atom for that matter, any n for that matter, which is of order z. So this argument works for any n of orders. N is fixed. But to any n, there is a mu. Right? To any n, there's a unique mu, so that when you minimize this thing together with that thing, it's the reduced Hartree Fock minimizer for that n. And this term here will then just be the, we'll just add in to give you the minimum of that energy. Yes, that's right. But because it's a convex functional, there's a one-to-one correspondence between the n and the mu. Right? So you originally fix the n. The n corresponds to a mu, so that when you minimize this thing here, without restricting the number of particles, then in fact, the thing you're getting with these two terms will cancel. That's how you choose. Right? And there's a unique mu that does that. That's the usual thing when you use it, put in a Lagrange multiplier. So did I explain it well now when you asked the question? Thank you. Okay. So in the end, we end up with a reduced Hartree Fock as a lower bound, with an error that we're getting by choosing the best A here, and that A is, well, I just put it to be z to the -3/4. I don't know what the constants are anyway, so the point is it goes like z to the 7. And I emphasize that what I really would like to have is that it's better than c². But I do mention down here that you can actually get it to be z 5/3. So 5/3 would be better than 7/4. You can do that calculation in your head. 3 times 7 is 21, and 4 times 5 is 20. So it doesn't look like it's much better, but an enormous amount of work went into going from 7/4 to 5/3, because 5/3 is the sharp bound. Right here, 5/3 is the sharp. I will discuss later on what little o, how to get little o of z 5/3, but then you have to add corrections. So at this level, there will be correction terms if you want to go for. Okay, so I put it down here. What have we proved? We have proved that the quantum energy, and I'm being a little bit imprecise here, this argument up there really requires that the n is of order c. So just think of the neutral atom. We proved that for the neutral atom, this difference here goes like z to the 7. This is also true if n is much smaller, but then it's a very bad bound. Okay, so let me say that we have actually proved this for all n, but we're interested in it for n being of order z and n equal to z. And you see we have a lower bound here in terms of reduced Hartree-Fock. And we also know that reduced Hartree-Fock is bigger, right? So we know that the quantum energy is the difference between these two is of order z to the 7th. It's actually of the order z to the 5/3, but I'm not proving that. Okay. In order to understand the z 5/3 and understand these values even better, we have to do Thomas Fermi. So that's what I'm getting. So I think Robert explained Thomas Fermi theory. I'll do it again very briefly, and then also explain how you actually prove the Thomas Fermi approximation. But in Thomas Fermi theory, what we do is we will replace the kinetic energy, which up until now we have not approximated. We have just used it to be the Laplacian. Now we want to change it. We want to approximate it so that it depends only on the density. And you recognize here the integral rho 5/3, which is the bound we had as a lower bound in the leap theorem. We didn't get this constant necessarily in the leap theorem inequality, although that's conjectured to be the right constant, but we don't know. But here we want to use it both as upper and lower bounds. We want to really approximate the kinetic energy by integral rho 5/3. So where does it come from? Well, it comes from a semi-classical phase-space integral that we say that we are actually calculating the energy by integrating 1/2 p squared over a region in phase space. And that region in phase space is determined by p being less than or equal to some f. That's called the local Fermi level. And the f is chosen so that the density, when I repeat the integral up there with a 1, and not integrating over x, that will give me a function of x. Rho of x is related to the f of x through this identity there. And if I then plug it in, calculate this integral, that gives me this if I plug in that value of rho for the f. So that is what's called the semi-classical approximation to the energy when you know the density. To the kinetic energy when you know the density. And then you plug in this term instead of the minus Laplacian, and you can now express everything in terms of the density, the attraction to the nucleus, and the electron-electron repulsion, keeping only the direct term. Remember, we had the direct and exchange term in Hartree-Fock theory, but here I'm keeping only the direct term. So let me just remind you what theory that describes God, everything that is present. Then you have that everything and finally, we have given a star, you can calculate gamma star, as the whole star, and if you don't have a gamma, then it's calculated the whole. So every time you go a level down, what's usually something is slightly reacted by the physical object. The most complicated is fully anti-symmetrical. This you can write down as one part of it. Take it all essentially. And you can try to express the energy in the model that you can only have higher density. Gamma that after that, all understand. What we talk about more complicated density function when we express the energy point of the density. in much more complicated ways than in Hartree-Fock theory, so in Thomas Fermi theory. But Thomas Fermi theory, with this functional there, is sort of the mother of all density functional theories, or the, if you want, the simplest density function. But now you do exactly the same thing as we did before. You calculate the energy as we did before. So the sharp up there can now be a TF. And I calculate ETF Z of n by minimizing this new functional over all densities that are non-negative and integral rho v. What is really nice about it is that this integral rho 5/3, the power 5/3 is bigger than 1. And that means that this is a convex expression in the density rho, because it lifts up, it raised to a power bigger than 1. This thing is linear in rho, it has a minus sign, it's linear in rho, so then it's still convex. And this thing here is also strictly convex because 1 over x minus y had positive Fourier. So as a function of the density rho, the Thomas Fermi theory is a strictly convex function. But more is true, it has a perfect scaling. And this scaling is really important in order to understand the structure of the atom. If you scale the density at Z, and here I'm thinking of, well, at this point I don't even have to say that. Well, I guess I do. What I meant here was we look at the neutral atom. Right? Because if I did not look at the neutral atom, there would be an additional parameter, which was the number of particles. So here, all I'm saying is that if I take this scaling, I define rho z of x to be z squared rho 1, z to the 1/3 x, then I get this expression that the energy goes like z7. Of course, I haven't told you what rho 1 is, so I could say, I was in my head thinking of it as being the minimizer for the neutral atom, but actually I didn't have to think of this. I could also think of it as a minimizer for a certain particle number, and then the scaling would, in principle, still be correct. I mean, this is just a fact that if I scale any function rho 1 to define a function rho z, then the energy will go like this. This you can simply check yourself in this expression. So here you see, so let me now think of the neutral atom. And imagine that we have a minimizer for the neutral atom. Then you see that the neutral atom scales like z to the minus 1/3 x, meaning that if you have the atom with z equal to 1, and you increase the z, then the density will behave like, I mean, the value you would have to put in here to get the same value there would be of order z minus 1. So the atom scales like z minus 1. Right? So the scale on which the atom lives is z minus 1. But it's slightly misleading, as I will come to, because you may now think that atoms shrink in size, like z minus 1. If you remember back to when we discussed hydrogen, hydrogen scaled like z to the minus 1. But there I also explained that because you fill in lots of electrons, it's true that every orbital in hydrogen itself scales like z minus 1. But if you go up to an orbital number of order z, then that may not necessarily scale like z minus 1. In fact, that will scale like z to the minus 1/3, just like the Thomas Fermi theory. I haven't proved that, but I'm just saying that it can be slightly misleading to think of these scalings, and I'll come to why it's misleading in Thomas Fermi theory to necessarily think of the atom as scaling like z minus 1. The bulk of electrons will scale like z minus 1/3. But the last electron will not scale like z minus 1. So let me try to explain. I'll get to it, but let me first summarize then what we know. So the function that takes n to the energy is strictly convex and decreasing up to some n less than or equal to z. I will prove this in a moment. We know that it's a convex function, right? Just because the functional was convex. So then this thing here will be a convex function. We also know that it's decreasing. That's essentially the same argument as it was for all the other models. But I will come to the fact that it is strictly decreasing for n less than or equal to z and constant for n greater than or equal to z. That's saying that this critical particle number in C is exactly z in Thomas Fermi. In Thomas Fermi theory, you cannot bind more than z electrons. The minimizer is unique. That's because of the strict convexity. I mean, the minimizer, for when it exists, is unique. And we have a scaling which behaves like that. In general, so this actually came from up here, if we allow the particle number not looking at the neutral atom, but an atom with the number of electrons scaling like z, say that you put in half the number of electrons that you can, so that lambda is 1/2, then you can still use the scaling argument up there, and you get that the energy is z7/3 of the energy of the atom with z equal to 1 with lambda power. Right? So the atom with nuclear charge z with lambda z electrons is really the same as the atom with nuclear charge 1 and lambda. And lambda here need not be an integer. There's nothing any longer in Thomas Fermi theory that requires that it is an integer. It's just the integral of rho. Right? That's what I put there. The integral of rho is the number. Okay, let's think about the variational equation. So let me go back up again. Let's find the Euler-Lagrange equation for minimizing this with a fixed integral of rho. Right? So it's again a constraint. I again have to do the Lagrange multiplier, put in a chemical potential. When you integrate this thing here, you will get 5/3 rho to the 2/3. When you differentiate here, you will get 5/3 rho to the 2/3. Here you will get minus z over x, and here you will get rho convolved with x to the minus. So this has to be 0, or rather it has to be mu if you have a chemical potential. When you fix the integral of rho, so you have the constraint in it. But you have to be slightly careful, because if rho is 0, so when I do the variational problem here, and my rho is 0, then I can only do a one-sided variation, right? I mean, if rho is 0 somewhere, if I'm in a region where the density is 0, I'm not allowed to subtract something from 0 because the density has to be non-negative. So at points where the rho is 0, I can only add something. So you will actually get an inequality that tells you something when rho is 0, or you will get an Euler-Lagrange equation that tells you something when rho is 0 and something else when it is positive. And that's what we're getting down here. So the rho 2/3, that came from taking the derivative of the kinetic energy. Forget for a moment the plus here. You know, this has to do with what I was just saying, that when it's 0, you can only vary in one direction. Forget it for the moment. Imagine we just did the variation. Forget also the mu. Try to explain it this time. Forget the mu. We're doing the absolute minimization. Right? We're not restricting the particle. Then you would get that the derivative of the kinetic energy, which is rho 2/3, is equal to z over x minus rho star x to the minus 1. Those are the derivatives of the other two terms, right? Of those two terms. So that's the equation you would get. Now you have to worry about the fact that maybe you are looking at a place where the rho has become 0. And then even if mu is 0, you cannot do the variation to both positive and negative rho. Right? So you can only do the variation in one direction. So meaning that if rho is negative, if rho should at some point have become 0, the only thing you know is that this thing here must have become negative. That's what it tells you, that there's an inequality at the end. And that inequality is exactly expressed in this all-Lagrange equation. And the mu was the chemical potential that you're adding in to do the constraint. Okay, I'll come back and analyze this equation in a second. This is called the Thomas family. So this is of the the self-consistent equation is what it would usually be called in the physics or chemistry literature, right? The self-consistent equation for the things. Right? The potential you are getting, the mean field potential you are getting, where the electron sees all the other electrons, is precisely such that it reproduces the density you start with. And this reproduction of the density is what semi-classical. Semi-classical. I'll get to that in a minute. Now, it turns out that, again, we have a perfect scaling for this, that you can simply read off from up there, right? That if you plug that in and do the integrals, in fact, this mean field Thomas Fermi potential scales like z to the 1/3 x, z to the 4th x. Notice that the first term has exactly this behavior, right? If I calculate, if my nuclear charge is 1, so that this term here would be 1 divided by z to the 1/3 x. Right? Then when I multiply by z 4/3, the 4/3 in the numerator will go out with a 1/3 in the denominator, and you would get a z over. Right? So this term has exactly this scale. And it's easy to see that this term there, using that scaling, also has exactly the scale. So again, the atom goes like scales like z to the minus 1/3, but then the potential goes up with z to the 4th. Okay, so now let me come to the fact that the critical n for Thomas Fermi theory is exactly. And we will conclude that from the Thomas Fermi equation. So let's look, so here I should actually have written rho strictly bigger than 0, because I wrote there on the set where rho is bigger than or equal to 0, but rho is always bigger than 0. I mean, on the set where rho is strictly bigger than 0, because on the set where rho is strictly bigger than 0, I know I can forget the plus. I know that this thing here must be positive, because otherwise I could not get something positive on the other side. So on the set where rho is strictly bigger than 0, I know that the Thomas Fermi potential is bigger than or equal to mu, and the mu is bigger than or equal to 0, because the thing here is negative, it's decreasing. So since the energy is decreasing, the mu is really related to the derivative of the energy with respect to n, and that's actually no. So from the fact that we know the curve is negative, that the curve is decreasing, has negative slope, we know that the potential mu must be bigger than n. So what does that mean? That means that at points where rho is strictly positive, the Thomas Fermi potential must be positive. But what do I know about? I know the expression for it, right? If I go back here, it's z over x minus rho star x to the minus 1. Right? But rho star x to the minus 1 is, if I think in terms of the Newton theorem, right? When you calculate the potential of a density rho, and you're sitting at some point, then at that point, everything inside the ball where you're sitting is like putting it at the origin. And all the thing outside, well, okay, it will give a positive contribution. We know what it is, but it's a positive contribution. Right? So in fact, this term here, what I'm subtracting there, must be less than if I took the charge inside and put that at the origin. And that's the inequality I'm using right here. The fact that the first term, so I'm sitting at a ball of radius r, the first term is z over r, and the rest, I would have, if I subtracted everything outside also, I would get the Thomas Fermi potential. But if I only take what's from inside, it's like putting the whole chart at the origin and divide by. So I know that phi from a Fermi theory is less than this. But then you see, I know that it's greater than or equal to 0. So therefore, this integral must be less than or equal to 0. Right? So if you have a solution to the Thomas Fermi equation, then the integral must be less than or equal. Now let me do it the other way around. Let me also show that it must, the neutral point, I mean, there are solutions for n being less than or equal to 0. I now want to show that the smallest you can get is actually all the way opposite. Right? So imagine that if I do the unconstrained minimization, that's putting mu equal to 0, right? It's the absolute minimum. I want to show that then n must be equal. So how does that go? So imagine that it's less than z. So imagine we had n less than z and mu equal to 0. Then for large x, if I go back and look at the equation here, so now mu is 0, and this integral, this function here is that function. And if the integral of rho is less than n, the integral of rho is equal to n, which is less than z, then when you go very, very far out, you see a nuclear charge screened only by n electrons, so there's something left. There is this thing here for large r will actually go like z minus n over x. You have a nuclear charge z, and then you have a charge around it that integrates to something less than z. But then as you go very, very far out, it will behave like z minus this total charge at the origin, like put at the origin, and it will go like z minus n over x. So in other words, imagine that n is less than z, then you would get this behavior for phi t f of x. But then let's go back to the equation again. Right? What was the equation? The equation was that rho 2/3 was phi. I now know like phi behaves like 1 over x, but that means that the rho goes like x to the minus 3/2, but that's not integrable. So then its integral cannot be n, but it would be infinite. So in that way, you see that it's not consistent that n is less. So in other words, the minimum is exactly. So this is a strictly decreasing and convex for n less than or equal to z, and constant for n bigger. The slope is minus mu at every point, and it becomes 0 when n is equal. And the strict convexity comes from the convexity. Okay, so now let me really specify the neutral TF atom and the slightly surprising fact that the atom actually does not shrink, even if we have this funny scaling of the z to the 1/3. Like we had this scaling there. It looks like the atom is scaling like shrinking like z to the minus 1/3. I mean, these things are always a little misleading, right? That this is actually saying that if the rho 1 lives on some scale, then the rho z lives on the scale z minus 1/3. It's always confusing that it says z to the 1/3 in here. That's the same as in the summertime, we have to move the clock one way. Whatever. You know what I mean. So I want to explain why this does not necessarily mean that the atom. Okay, but let's look at the neutral atom. So for the neutral atom, same argument as before, rho star x to the minus 1 is always less than or equal to x minus 1 integral of rho, of all of rho, right? That's because, that's Newton again, right? If I'm sitting at some point, then everything which is inside, it's like putting it at the origin. But everything outside is actually small. It gives a contribution that's smaller than if you would put it at the origin. So the rho star x minus 1 is actually smaller than what you're getting by putting the full mass. We used that inequality earlier also. That's the same as the one that said that W of A was less than x to the minus. So that really means that for the neutral atom, I can ignore the mu is 0, and I just argue that this thing here is always greater than or equal to 0, so I can ignore the plus. So in other words, the equation just looks like that. There's no plus over here anymore. Much nicer equation for the neutral atom. And I can now rewrite this thing here as an equation only for the function phi. And why is that? Well, that's because recall that the phi was this was z over x minus rho convolved with x to the minus 1. So if I do the Laplacian of phi, I get something with the delta function at the origin. But outside the origin, I get the density. Laplacian of phi outside the origin is rho plus rho. So it means that I can, instead of writing, so I can put the 2/3 on the other side, writing it as 3/2, and then use the fact that this thing here is a constant times rho. So outside x equal to 0, I get this nonlinear elliptic equation for the Thomas family. And notice that there's no z in here, because I'm looking at this equation only when x is different from 0. If I want to remember the z, this is something that happens at the origin, and that would mean that I should add a delta function to this equation. But I don't want to do that. I want to look at this away from x being 0, and then I'm getting this equation here, and I'd rather like to think of the z as being a boundary condition at 0, that the potential phi goes like z over x near the origin. So just to go back again, this was the phi near the origin. It has a singularity of order z over x. But away from the origin, it satisfies this equation. So I want to think of the z just being the boundary. And if you plug in all the constants, you're getting this 3 root 2 square root, 8 root 2 over 3 pi. And here comes the funny thing for this equation. People have actually studied these types of nonlinear elliptic equations with singularities at a point. And asked, equation, what I meant by singularity means that you're looking at equation like this away from one point, here the origin. And there's a theory for what's called weak and strong singularity. The weak singularities for this equation here is the z over a constant over x. So there are solutions to that equation with a singularity z over x for all z greater than or equal to 0. This we know already because these are the Thomas Fermi. We know that the Thomas Fermi problem satisfies. But there are also something called strong singularities, which are sort of have a certain type of universality property, which is a much stronger singularity at the origin. In fact, it's the function that goes like bx to the minus 4. Let's just check that something like this can solve, or actually will solve, that equation. Because when you do the Laplacian of x to the minus 4, you're going to do true derivatives, so you're going to get a constant times x to the minus 6. But x to the minus 4 to the power 3/2 is also x to the minus. Right? So there is a b, so that a nice looking expression like this actually solves that. Now you might say, oh, but what then happened with all this? What about all this scaling and so on? Does this still satisfy the scaling property, this equation? And in fact, it does. Remember the scaling property of the Thomas Fermi potential, which was z 4/3, z to the 1/3 x, z to the 4/3. Notice that any function like that is exactly a fixed point for this scaling. Right? If I do the z 1/3 x to the minus 4th, I get z to the minus 4/3, which cancels. Okay, but does this mean anything? Does it have any importance? Is it just a mathematical curiosity that this is also a solution to that equation? Well, it's much more than a mathematical curiosity, because you can analyze the Thomas Fermi problems, the one with weak singularities of order z over x at the origin, and you can actually prove that at infinity they behave like this. So no matter which z you choose to solve the equation at the origin, then at infinity it will be, and that's why I called it universal, it will have the universal behavior of this b x to the minus 4. You can calculate the b yourself. Right? It's a universal, it's 1b, doesn't depend on any. And all the Thomas Fermi mean field potential, they scale like this at infinity. They scale like x to the minus 4. Remember, I'm doing the neutral atom. Right? So the neutral atom has the property that if I move away from the nucleus, I have more and more charge inside my ball, so I'm more and more screening the nucleus completely. So it no longer behaves like 1 over x, which is what I would get if I did not screen the nucleus completely. It screens the nucleus more and more, so it actually goes like x to the minus 4. And if you plug that expression into the expression for the density, you find that the density goes like x to the minus 6. So the density will also have a universal behavior at infinity and go like x to the minus. So in fact, the atom does not shrink, right? Because if you go very, very far out in the atom, all the atoms look the same. The bulk of electrons, if you integrate the density and ask, when have you come up to half of z electron, that will scale like z minus 1/3. But if you ask, when is the last electron, right, that's the one I used to define this radius, where's the last electron? Well, that does not decrease. So in fact, atoms in Thomas Fermi theory do not become smaller like z minus 1/3, not if you define the size by asking where is the last electron. So there's another property as well, and that is that that's the reason why I put an infinity here. Infinity could be because it had a strong singularity, but in fact, it also turns out that point-wise at each x, if you analyze the Thomas Fermi mean field potentials and let z go to infinity, then they actually converge to x to the minus. I mean, that's not so surprising if you think of the scaling and the fact that they behave like that. So the x minus 4 appears two places. It appears always as the tail in the mean field potential, but it's also what the mean field potential will converge to point-wise as x goes to. So the atom, in a sense, does shrink like the bulk of electrons shrink like z to the minus 1/3, but it's just as it shrinks, it just reveals this tail, x to the minus 4, which is universal. So when you let z go to infinity, it will actually converge to this x to the minus 4. Right? If you pick a point x independent of z and let z go to infinity, then z minus 1/3 is shrinking, and you will see the x bar. So that's exactly this property. Maybe let me go real fast back to I told you I was very proud of this numerical calculation I had done right there. This curve here was exactly calculated by asking what is the radius in Thomas Fermi theory so that there's one electron outside. That does not, as I explained to you, does not decrease with z. In fact, it looks like it increases. But what I have just argued is that it actually converges. You just do not see the convergence. And actually, the numerics is a little tricky to do. So I don't quite know how far out you have to go to really see it. But it's very large. It's z of order 3,000 or 5,000 or something before you start seeing really becoming. Okay? But the interesting fact is it does not decrease. It actually increases. And this curve was calculated using Thomas Fermi theory out to where the last electron. So let me use this to introduce one other model that I will come back to later, what I call the mean field Thomas Fermi. And the reason I want to do this is that, well, it's very nice that Thomas Fermi theory converges. But I have kept asking about this periodicity of the large periodic table. But if everything converges, that is sort of against what I said before. Before I said that I would expect convergence through sequences and not convergence in general. But Thomas Fermi converges. The density converges. This is the phi to the 3 half. x to the minus. The radius converges. So where, if there is any periodicity, you do not see it in Thomas Fermi. But there is another way to look at the problem, which is slightly better than Thomas Fermi theory. And that is to actually look at the mean field operator, exactly the one we described earlier on, right? The one that here takes the z over x minus rho star x minus 1 with Thomas Fermi. Right? That is the Schrödinger operator for the electrons moving in a potential created by all the other electrons and itself, unfortunately, if you use the density as the Thomas Fermi. And now you may ask, oh, what happens if I now start filling electrons in here? So I use this as my Hamiltonian for here. And this I call the mean field Thomas Fermi. And actually it does correspond a little bit to what is done in density functional theory by chemists. They also have a strategy that when they have found a minimizing density, then they actually go back and do something similar to what I did here. And this is what they call the Quantissima theory. And then they find a density matrix as a minimizer. So this procedure of going from the row to a one particle density matrix by writing down a mean field operator is used a lot in chemistry. So I'm almost finished. I just wanted to say that, I will continue the study of this Thomas Fermi mean field theory, but I can do exactly the same argument as I did before for the lower bound. Remember, I have the choice of choosing the rho tilde any way I like. So I could also choose the rho tilde to be the rho Thomas Fermi. And if I do this, I actually get this lower bound. Same lower bound as we had before. This is the correct lower bound on the quantum Hamilton, written in terms of the Thomas Fermi mean field theory. So for all I know, the Thomas Fermi mean field theory is as good as reduced Hartree-Fock. Probably is not quite as good, since I somehow knew that reduced Hartree-Fock was the best in this lower bound, but I don't really have effective ways of estimating. So this is actually a really, really good term. But it was just the lower bound. And you may ask, what about an upper bound? Is it actually true? Is this the correct upper bound? In reduced Hartree-Fock, I knew it. It was trivial that reduced Hartree-Fock was an upper bound. Now it's no longer true because it's asking how good an approximation is Thomas Fermi theory. But you can prove, but I will not do it here, but you can prove that in fact, if you take the psi here, which is the ground state, then you actually get something which is less than or equal to the sum of all the negative eigenvalues of that operator with that constant and an error here which is even better than the 7/4, which is the 5/3. I already said also that for the lower bound you can also prove 5/3. And here I just claimed the 5/3 because I'm not going to prove that. It's usually easier to prove upper bound because you just have to guess a good trial function. It's not such a trivial computation here, but it's not difficult to understand what you should do to prove